Welcome back to the Foundry by Forge College. Okay, let's dive right into this explainer. If you remember our previous lesson, Framing the Capstone, Gulfstream, and Transaction Goals, we did a fantastic job mapping out our transaction flows. It looked beautiful on paper. But listen, before we jump in, write a single line of test code, and let's be real, inevitably realize we just broke absolutely everything, we need to stop. We have to draft our architectural testing blueprint. Because designing a proper Foundry test strategy, that's the critical bridge between just kind of knowing how to write a basic test and actually building a comprehensive enterprise-grade suite for our Ethereum dev stacks and frameworks capstone. So how exactly are we mapping this out? We're going to build this engineering blueprint using the rule of three. We'll be looking at Pillar 1, scope, Pillar 2, structure, and Pillar 3, success criteria. Now, you might be wondering, why go to all this trouble? Well, honestly, jumping from hard hat to Foundry without a cohesive strategy is literally like trying to build a physical skyscraper by just randomly gluing bricks together as you find them on the ground. It's totally chaotic, and it almost always ends in tears. A patent-level strategic testing approach actually forces you to do less work overall. It systematically prevents those hidden flaws that drain your ETH, and it makes your entire testing process organized, measurable, and incredibly fast. All right, let's get right into Pillar 1, scope, and specifically mapping out our test matrix. This right here is where we inventory exactly what needs to be tested. You can think of the test matrix as the absolute holy grail of your blueprint. Rather than just guessing what might break, we deliberately map our contracts, things like the vault, the token registry, and the liquidity manager, directly against the exact types of tests they require. We allocate specific estimated counts for our unit, fuzz, and integration tests. This ensures we get perfect coverage without wasting hours and hours on completely redundant checks. Let's talk about fuzzing for a second. Think of a fuzz test like handing your keyboard to an incredibly energetic toddler, letting them just bash away and seeing what breaks in your smart contract. Sounds terrifying, right? But the trick is, we use the VM assume cheat code to kind of constrain their inputs. It acts as a safety net. This keeps the testing heavily focused on those tricky, relevant corner cases rather than letting the fuzzer break trivially invalid things that our require statements are already going to catch anyway. Next up, we have the forked regression test. This is the part where we verify how our smart contracts gears actually mesh with live protocol contracts out in the wild, like real liquidity pools sitting on the mainnet. Basically, we clone the live state and run our tests directly against it. But a quick warning here, because they interact with massive external states, they are painfully slow, for sure. So strategically, you want to keep these minimal and highly targeted. Okay, moving on to Pillar 2, structure. It's time to talk about organizing our files and fixtures. We really need to figure out where all these blueprints belong so our developer workspace doesn't just evolve into a cluttered nightmare. A disciplined folder layout brings immense speed to your workflow. We use the src directory for our contracts and test for our Foundry tests. Standard stuff, right? But here is the secret sauce. Any shared expensive initializations absolutely must live in a dedicated test/utils folder. Isolating your complex setups right there as reusable fixtures will massively speed up your runtimes. And finally, we keep a bench folder to hold all our gas harnesses. So how do we guarantee these tests are completely reliable? We look to the beating heart of the test files, the setup function. By combining setup with Foundry cheat codes, like using vm.deal to fund accounts with ETH or vm.prank to simulate specific senders, we create a deterministic, perfectly isolated testing environment. Every single test starts from a completely clean, mathematically predictable slate. No state leaks, no surprises. Which brings us to our final core concept, Pillar 3, success criteria. Let's look at setting up those CI gates. Ultimately, how do we mathematically know our metaphorical skyscraper isn't going to just collapse the second we prepare for deployment? We need strict automated gates. For example, we anchor this with a very specific performance metric. We demand there is no more than an 8% gas regression versus our baseline commit. That means if you add a new piece of code and it causes our hot path to cost 9% more gas, the entire test suite fails, hard stop. It's an absolute ceiling that ensures our optimizations never silently degrade over time. And this strictness, it extends right across our continuous integration, or CI gates. We break our measurable gating rules into 3 distinct categories. First, functional, meaning absolutely all invariants hold true. Second, quality, where we demand an 85% minimum branch coverage. And third, performance, ensuring our gas deltas always stay below our thresholds. By doing this, that subjective, fuzzy feeling of I think the code is ready, transforms into hard, objective, mathematical reality. All right, let's wrap this up with the execution workflow, taking this from a pure strategy all the way to automation. It's time to pivot and actually put this blueprint into our daily developer rhythm for the comprehensive Foundry testing suite, Capstone. Here's the exact linear progression for executing it. Step 1, inventory your contracts. Step 2, set up that beautifully clean folder structure. Step 3, define your strict CI criteria. Step 4, prioritize your tests. And hey, this is absolutely critical. Priority 0 tests, the ones that protect the actual flow of user funds, you build those first, period. Finally, step 5, automate the whole shebang in CI. If you follow this exact path, you will go from an empty directory straight to a battle-tested protocol. To close this out, I want to leave you with one punchy, unforgettable rule. A test is not finished until its acceptance criteria are met. Simply writing the code isn't enough. It literally has to pass the mathematical gates we just finished designing. So I'll leave you with a bit of a provocative question to think about. If you ran your current codebase through these 3 pillars today, how much of your supposedly secure code would actually survive the CI gates? To master these architectural skills, ensure your smart contracts never collapse, and dive deeper into advanced Web3 learning, head on over to forge.college. Thanks so much for joining me today on this explainer, and I'll see you in the next one.